All right there then.
Just get free massages.
I know, you can like be a volunteer.
Let's go ahead and start. So I want to know, what is the point of the stress egg and the stress kite? What are we doing with that? Yes.
We are seeing where the combined flow stress could be the lowest, so where we don't have to pull as hard to be able to deform the material.
Okay. Yes. So combined flow stress, I think, is good. Possibly trying to find out where it's least, or at least we're just evaluating the system to see if we have to increase the amount of stress that we're applying, or if we're doing something to take advantage of a way to decrease the amount of flow stress. All right. What did you see in the forging and forging videos? So like when it first upset the part, what did you notice about it? There's a lot that happened in that first few seconds. Yeah.
Like the outer shell cracked off.
Okay, so all of that fell off. That's scale, that is oxidation, and that is from the time that they take it out of the oven with the big forklift and they drive it across to the other side and they squash it. In that amount of time, it is a major amount of scale that grows on the outside of that thing. And you have to be careful of that scale. If you get those oxides pushed inside, they're ceramics because they're oxides, and if you get them pushed inside, they stop the matrix. It's bad. Then Neo comes out. But they are inclusions. They're big inclusions, and so they will cause a weakness and an internal fracture point. So you have to be careful what you do with that. What else happened? Yeah.
Got flattened from like more of a cylinder to more like a puck shape.
Okay. Yeah. So sort of squashed it down from a cylinder to a puck. All right. Yeah.
It barreled.
It barreled. So the edges pooched out on the sides. And that's because it would like to all move outwards by the conservation of volume, but it is stuck to the dies. And so because it's stuck to the dies, they squeeze it down, it has friction at the edges, and then in the middle it barrels out. When you do something tall and thick like that and you squash it down, it can barrel out. But if you were to take that same part and start it as sort of the ending diameter but with straight walls, and you tried to squeeze it again, it would be very hard for it to barrel out because of the ratio of the height to the diameter. It would do it a little bit, but not very much. So, yeah. Okay. Ring rolling. You watch ring rolling, right? Why? So the machine was complicated. They come over, they put this thing down on the machine, and then they start rolling it, and they're rolling it with vertical rollers over on one side and horizontal rollers on the other side. And because of that, the horizontal rollers have to keep moving back as the size of the ring gets bigger. It would be way easier to build that machine with the horizontal and the vertical rollers right next to each other so that you didn't have to have it moving and changing size as the ring grew. Why do they do that?
Was it because of, well, for one, Tresca's model, and then also just like it keeps it in a manageable place, like the plasticity of the metal in a manageable place.
Okay.
So it's not.
So tell me more.
Like, I don't know how to put this into words very well, but they don't want it to become outside of Tresca's model where it would just flow.
Well, no, you have to have it outside of Tresca's model to be able to deform it. If you're inside the stress egg or the stress kite, it doesn't, it deflects elastically, you let go and it returns.
Okay, never mind.
Well, but you're on the right path. You're on the right path.
Are we talking about how it's we have the vertical rollers and the horizontal rollers on two opposite ends?
Yes. Yeah, that's part of it. Yes.
Because when you have something that's compressing it horizontally and vertically, we're at that having like the positive and the negative stress, which means you can have a lower flow rate or flow stress to deform the material. So you're putting less force in to deform it?
Okay, we're more avoiding the point of having it, so we're putting more stress, or having to put more in.
Yeah.
If we had the vertical and the horizontal rollers right next to each other, we would be in a combined stress state, and we would have to do 1.414 times the amount of stress to be able to deform it. But by separating those two, we put them where all we have to do is achieve the flow stress, because we're only going in one direction. Now, it's not quite that easy, because there's a little bit of sticking to the rollers, which prevents it from getting wider, but not a lot of friction there, and they had the happy person with the big long stick of lubricant that they were spraying on it. I think it's kind of hilarious that they have this machine where everything is automated on the machine, but somebody's got to hold the stick and spray the coolant on. Really? You couldn't figure out a way to have a machine hold the stick? But anyway, it's good. It job security. Okay, there's another reason. So besides finding the best place on the stress egg, there's one other reason to do deformation on one side and the other deformation way on the other side. It has to do with hot work.
I think that if you have an operation that's squeezing material, it's creating heat, and if you have them right next to each other, they have a whole 360 degrees to go until it gets reworked again, so it has an opportunity to cool down. But if you're constantly manipulating material, I think that maybe it's quicker.
Yeah, if it were plastic, that would be true. But because it's metal, you're actually taking out more heat when you're rolling it. You are doing work on it, but the rollers pull heat out, so it doesn't actually significantly add or remove from the heat. It is about heat.
It would become like too ductile if you.
No, the other way. So if you squeeze it and you work it, it will, for a very short amount of time, be strain hardened. So you're going to cold work it or strain harden it as you deform it. If you immediately tried to deform it in the other direction, it would still be strain hardened, and you would have to work really hard to be able to deform it. But because it is hot work, it is constantly recrystallizing. So by the time it has gone over to the other side of the circle and you're mashing it there, you've had enough time for the recrystallization to happen and a bunch of diffusion to happen, and then over on the other side, it's working with material that's at the base conditions again. So, yeah, stress egg and hot work. You can just about answer stress egg and hot work for anything. Occasionally throw in constancy of volume, and that'll answer most of the questions. But you have to understand what you're doing with those. Oh, yeah. So as the work was being done, instead of taking the thing, they could have done it a lot faster, right? They could have just taken the whole thing and just gone and squashed it when they were making the big long stick. But instead of just squashing the whole thing, they did it in little tiny squashes. They worked their way along it, then they flipped on that side, and they worked their way back out there to the other end. Why do they do it in a bunch of steps? What are they doing? Yeah.
Was it because if they like did one giant squish, there would be more chance of the part deforming overall, and versus if they do it in little tiny squishes, it's like more uniform in those small spots?
Okay, so they're able to control it better, and it means that it will squash the same way all the way along the length, whereas if you squash the whole thing, the ends, which are free, would squash differently from the middle, which is constrained by the ends. So that's some of it. Yeah. Yeah.
If you squash the whole thing at once, there'd be like a lot of friction along the surfaces, so and not like be able to deform it as much as you want.
Okay, yeah, so if you squash the whole thing, stress egg. If you squash the whole thing, you have a bunch of friction. So you get down here at the 1.15 times the flow stress that you have to achieve. So you've made the problem harder, plus you're squashing along the length of the whole thing, so you have a bunch of contact areas, so the kind of force that you're having to generate is massive. So that's another reason. And then there's one last one, similar to the ring rolling. If I deform it here, then I move over and I deform it, I move over and I deform it. By the time I get to the end, the place that I started has had a lot of time to recrystallize and go back to the original conditions. So when I work it on its side and work my way back out, when I get there, it is soft again. And so it just makes it easier to control from that standpoint. Okay. On that, remember, they were making a long stick. It looked like they were making a telephone pole by the end. A metal telephone pole, a really heavy metal telephone pole. But they started out by making like a hexagon or an octagon or a something-agon, right? They squash it, they rotate, squash, rotate. And then at the very end, they came in with the circular dies and they made it actually be cylindrical. Why didn't they start with the cylindrical dies earlier? Why not just get there from the beginning? Why do, because they had to go really slowly, squash it, rotate it a little so it wouldn't pancake.
I think it's just the edges and the radius, they have a lot of material to squish in, whereas the tops wouldn't really have much radius, or like, have that much deformation.
Okay.
So you kind of get the general shape, and you let it recrystallize, then you can go for your final diameter.
Okay, so there is some that it would put a bunch of load on the edge of those dies and none in the middle for a long time as it tried to do it. Okay, that's good. What else? Yeah. No?
Well, which one are you pointing?
I don't know.
Oh, Kayla, you go.
Huh?
You're
No, I didn't.
Oh, I thought you did.
Sorry.
That's okay. Wasn't it, so it could achieve like directional grain flow before the rollers came in?
Yeah, you might be able to do that. It's a little hard to say because it was all hot work and they were leaving it a long time, and so the grain probably would have regrown. So it's hard to say if the grain would actually retain any structure to it or any texture to it. I don't know that. What's that you said? The stress egg? Absolutely. That is exactly the right answer. I'm so glad you said that. Think of this. Yeah, there you go. All right. So it is an egg. We'll get there. So you have the die that looks like this. When I squash the piece of material, this die is pushing down and it's pushing inward at the same time. So those are fighting each other. If I'm pushing inward while I'm trying to push down, I'm making my life harder. I have just achieved 1.414 times the flow stress.
Do I need to know that?
Yes, you do. It's in the video, you'll get it. When you have a chance to not spend the night in the hospital. Try to not do that.
It's expensive.
I'll practice.
Yeah, this makes better. All right, so if you are squishing it in multiple places, you made your job harder. And so what they're doing is they are delaying this until the very last moment. Also, if the part is really big and you're trying to make a small shape like this, you would have to have dies with a bunch of different arcs in them to bring it smaller. So you'd have to be changing out dies all the time. You'd have to buy a bunch of dies. Plus, a really big die with a big arc in it is super hard to make because they have to be really strong, and it's hard to make them that strong. Questions about that? Okay. No questions. So you're ready for the quiz? We're not going to have a quiz right now. But
I was about to have another hospital trip.
why is forging, like we saw in the video, done as hot work? Yes.
I have a crazy guess. Is it the malleability of the material?
Is it the stress?
Malleability. Malleability is good, but let's go to an engineering term, a material property term for malleability.
Ductility.
Ductility, that's right. Because when you take something that big and you're changing its shape as much as they were, that's like 200 or 300% strain. They are completely changing the shape. Metal will be cold work. Most metal tops out at somewhere between 20 and 30% ductility, and then it's going to shatter. And so by doing it as hot work, they can completely reform it by several 100%. And so you can completely change its shape because it's continuously renewing its ductility and giving you the ability to reform. Nope, we already answered that. So there are other really cool things that you can do here. This is a crankshaft. So in an engine, this is the thing that goes round and round, makes the pistons, well, actually, the pistons go up and down, little explosions happen up here at the top that power the pistons downward, which makes the crankshaft turn, which makes the thing go or generates electricity or whatever it is. And the thing that's really cool about that, or really difficult, is that crankshafts are super hard to create. They are under a tremendous load. And they are weird shapes with all of the journal bearings being way out to the sides on them. And so it's hard to make them strong enough so they don't fail. One way that you can do that is to forge them, and while they're hot, you forge, so you start out with a stick, you hit it really hard with a hammer till this thing is offset way to the side. And when you do that, the grains will have this flowing around the edges. And if you quench it really quickly to lock that grain pattern in there before it is allowed to recrystallize, what happens is at these corners, all of these corners are stress risers to some extent. And what we've done is take all of the grains and form them around that corner to back it up, to make it stronger so that the material won't crack at those edges. And so that's pretty cool to be able to do that, to form that grain out of the same material that normally might not have been able to do this. You can now give it extra strength by forming the grain against the direction of the crack.
How does a crank typically fail in terms of its grain direction?
In terms of its grain direction.
If it's going around the corner like that and has a really nice organic sweep to it that's following the direction of like the material, will it fail perpendicular to the grain direction? Does it fail?
I would say that, well, so this helps.
Yeah.
But it doesn't, it's not perfect. And it requires that this not have a stress riser. If you have a sharp corner right here, it doesn't matter what you do with the grain, it's going to move its way through. And so if there's a manufacturing issue or if it gets dinged, that will do it. Yeah. The main way that cranks fail actually is that they don't get lubrication around their bearings and then they seize in the engine block. Yeah. Okay, you can do this with cold work too, it turns out. So when you put threads on a bolt, most threads are cut into the bolt. When you cut them into the bolt, they're cutting through the grains. And so internally, if you were to look at the thread, it looks like this, and the grains are in the direction of the bolt, depending on how it was created, and we just cut through all of them. So right here, we have a big stress riser, and it doesn't really have any help from the grains to it. The cracks can kind of go off at a diagonal and find their way through the system pretty well. A different way to do this is actually cold work, but you can roll the threads into the bolt rather than cutting them into the bolt. And when you roll them in, then it will do a little bit of this forming of the thread of the grains so that they strengthen the threads on the bolt. We'll watch that a little sometime later. We'll watch how bolts are made and we'll discuss a little bit more about why we need to do that on the bolt. But anyway, it can be done. This is cold work. So because it's cold work, we're limited to 20 or 30% ductility. and so we just can't do that much motion on it, but all we're doing is creating these little threads, so we don't have to do a huge amount of deformation like the crankshaft where we were moving parts way, way out to the side. All right, forging is the first of the bulk forming processes that we're going to talk about. So you've seen open die hammer forging. That was what the video had, also some ring rolling. And so there are three terms that we use in forging or in deforming metal. They're important to know. The first is upsetting, that is in the video. And upsetting is decreasing the length, which increases the cross section. So just making it shorter, squashing it, and it's gonna pooch out on the side. The second one is drawing it out. That's where I grab the ends and I pull, and so it gets longer and the cross section gets reduced. And then the last one is squeezing. That's where I start to upset it, but I constrain it on the sides so that it just has to squish around and fill something like a closed die. So I am squishing it in one direction, but causing it to flow in the other directions until it fills the die. So those are three really important terms to understand and to use to communicate forging. So if I look at these, and I look at the stress egg, because we always look at the stress egg, where do these, because that's good, where do they fall on the stress egg? So let's talk about upsetting. If I squash something and it gets wider, where is it on the stress egg? Yes? No? This is where you answer. Yes?
Like right either at the bottom or on the left, like straight, which is being compressed in one direction.
Okay, so what is the distance from the center?
Oh, like one times the.
Okay, yeah. So depending on which axis I'm in, I'm either right here at the flow stress, or if I was doing it in the other axis, I would be right here at the flow stress. So there's a, yes?
Is that for upsetting?
That's for upsetting. Now, if I am upsetting and there is a lot of friction on the die, then I might move down the egg and get to the 1.15. And it's gonna be somewhere in that range, and that depends on the height versus the diameter and a bunch of stuff. But generally, that's what it is. What about drawing out? Where's my stress egg happiness for that? Just pulling on the ends.
Taking it go the other way.
Okay, where are the other way?
The other way of the arrow. Yeah,
Okay.
that like that.
So I'm right
exactly.
here at sigma F, or I'm up here at sigma F, depending on which direction I'm pulling it. And for the most part, that's all I have there, unless I decide to help it along and I squeeze it in the sides while I'm pulling it out. So that would get it more towards one of the shear areas. What about squeezing? So I'm squashing it, but I'm really not letting it move anywhere. Where does that put me? Yes?
Would it not move?
It does move. It's crazy. It does. Yeah. So we would be here, because it's the same as this.
Oh.
We're squashing down, we're squashing in from the sides, and so that's squeezing is going to be the 1.414. So I'm having to work way harder. Questions about that?
Wait, squeezing's at 1.41?
Yeah, squeezing is down here because I am pushing downwards and inwards with the die as I squeeze it.
Then why do we ever squeeze it?
Because we need to fill the die to make it the right shape.
Yes.
Yeah, so it just means, it doesn't mean it's impossible. It just means we have to work harder. So, okay, as long as I know I have to work harder, then I'm prepared. That's fine, work harder. three other terms that we use with this. One is cogging. So cogging is what we saw in the video. It's using little dies and going squish, 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 squish in little short areas. And remember, we talked about the reasons for that. One is that it reduces the amount of friction. So hopefully it moves us from this 1.15 sigma F back to sigma F, because we're reducing the amount of friction with the die just by having less area. It reduces the amount of force that we have to put into it just because we're contacting it over a smaller area. So it's a smaller force to achieve the flow stress. And it also allows other parts of the material to regrow or recrystallize their grains so that the ductility can be increased again. The second thing to talk about is edging and fullering. In fullering, we use a convex die. You squash it in the middle and it squirts out to the sides. Ooh. So where on the stress egg is fullering? Yeah.
1.414 because it's squeezing.
It might be, but it's not quite.
Would it be like less than 1?
Yeah, it's less than 1 because as I'm squeezing down, I'm also pushing outwards. And so it's like having an intention. If I were pulling it and squeezing, that makes it easier to deform. So I'm actually moving more towards this 0.707 area when we do fullering. Edging, we already talked about edging with this die. We're down here approaching the 1.414 area. Life is harder, but if that's what we need to do, that's what we do. We talked about barreling. We're going to go on. If we add friction when we're doing this, and we were to look at the equation, you don't have to know the equation, but something that's pretty cool. If we're looking at how much force do we have to have some amount of pressure times an area, we know that. When we have friction, we put this modifier in there called QA. And if we look at QA, what we see is some kind of interesting things. We see that it depends on the diameter versus the height, and there's a place at which nothing happens. It just, it sticks to the edges and it won't move. Further down here, it's gonna move, so as you squash it, it will move along the die and it will get bigger. But we have this line where it doesn't move. What did we say about friction last time? Talked about friction kind of ending in the way we talked about it in physics class. What was happening when we got to that point?
Shearing?
Yeah, it started to shear instead. So interior to the material, it's shearing sideways. So when we get to this line, when we squash it, it just sticks to the die and it starts to shear out to the sides and roll out. And that makes really ugly material because it has the part that stuck and didn't move, and then it has this material that rolled out to the sides, and it will have different material characteristics. This is if you are squashing something and you use really big platens. The platen is the thing that you use to squash it. If you have a really big platen to squash something, you're constraining it everywhere along the outside. It can't pooch out very much. And look at what we see in the equation. We have a 1.15. Where does that come from?
Stress egg.
Stress egg. It comes from right there. So we can see that that equation came from right here, and we know that if you use a big platen on a small part, there will be so much friction on the edges that it's going to require more stress to be able to deform the part. So that's another reason that we do cogging, because cogging required a smaller amount because we were minimizing the friction. All right, let's watch one of these happen. die hammer forging. Die hammer forging is where we squash the material into a shape. So we're gonna use a die that has a shape in it. We're gonna hammer the part, usually more than once. We will often have to preform the material first to get it sort of to the right place to get it to flow. When we do this, we end up with this little bit of material right at the edge that goes in the gap between the dies. And this is called flash. And it seems like flash would be bad because it's waste. Yes, this is good flash though. In injection molding, flash is always bad, I think.
Yeah.
It means your die is old and leaky, or you didn't have enough pressure to close it. It's always, you have to remove it. I don't know that it serves a purpose. Does it serve a purpose?
I think it's just more things that you could do to it.
Okay. So this flash we actually want. And the reason that we want it is, one, it prevents the two halves of the die from slamming together, and they're such strong metal that they're also very brittle. And if they slam together, they would explode. That would be bad because there's hot metal in the middle of it, and they're giant. But the second thing is, if I take this and I squeeze the material before I get the dies closed, the material would rather just ooch out the sides between the dies. And what the flash does is it's this thin little layer out here, and so it cools really quickly. And it makes sort of a belt around the part that prevents the material from ooching out between the dies when you close it. So it's preventing the dies from slamming, and it's preventing the material from ooching out. So that is a good thing. You can do flashless forging. It's really hard to do. Not many people do it. So when you're making something, you would start out with a stick. You would put it into one die that makes it into a preliminary shape usually, and then you put it into a second die that makes it the final shape. So let's watch that happen because it's cool.
Impression die forging accounts for the vast majority of all commercial forging production. The name comes from the specially fabricated impressions in the matched dies themselves. Although open die forging takes the honors when it comes to maximum customization, impression die results are within closer dimensional tolerances. They can also range from a few ounces to over 10,000 pounds, and from a fraction of an inch to over 26 feet. And if other processes are added at various production stages, the quality and production economy of the end result is further enhanced.
All right, let's look at something there in the middle.
Die results are within closer dimensional tolerances.
Okay, so there are three dies there, right? There are three impressions that they're putting things into. So starting out with a beginning shape, then flips it over to this far side, and then flips it back to the middle. You'll notice the hammer is coming down very repeatedly. This is the new version, which is safer because they can stop the hammer from coming down. In the old versions, the original ones, the hammer came down, there's a big crank up at the top. And the hammer came down every time the crank went around. Whether you were ready or not, the hammer was coming down. And so this is a much safer version. So he has a foot pedal that causes the hammer to come down, and you remove your foot from the foot pedal, and then the hammer will not come down. It just goes around. You still have to be super careful with this because these tongs, if he were to get the tongs too far in there so it closed on the tongs will come up and gut the person. So it is a very dangerous operation. You have to be, have to have really good concentration and really be careful about where you're positioning things. You can make the dies so that they help the person to not put the tongs too far in if you design them well. Also, an interesting thing that's kind of hard to think about with all of these is the weight that is going on. So that is a stick of metal being held in a pair of tongs, you know, several feet out. So it's probably like 30 or 40 pounds of metal that is just being held out there. You're holding it and putting it back into the die each time it hits, and then flipping it over and then flipping it back. Tremendous forearms. That's what this is.
Why would they not? Because in this one they go like 1, 2, 3 in the middle. Why don't they just go like across?
There must be a reason that it is easier to flip to the far side. I don't know exactly what it is. You could do it the other way, and they don't. So
Okay.
I don't know. So pretty cool. So this is how they made all of our connecting rods at Caterpillar. So we would get these from Japan, and the reason that we did them is because there's a huge amount of stress going into this thing very, very quickly as it's being formed. And if you immediately quench it after this, you lock a tremendous amount of strength into the materials. And so that was making ours much stronger. And it also formed, if you do it correctly, you can form the grains such that they prevent or they resist the biggest loads. Yes?
So when he like sends it off, does it like go into a water bath or something?
I don't know where his is going. And I would imagine that it is going into a tank of oil.
And then you like trim the part after using machine?
Yeah, they would trim it afterwards. You also probably have to take it from here and do a little bit of annealing on it, probably. But there would have to be a bunch of metrology and measurement to see if they've made the parts right before you would buy them.
Yes.
All that kind of thing, yeah. Okay, so when you are doing this, the graph of the force looks like this. So you first contact the part, so this is just the graph of this closing, and the amount of force that it's taking to forge it. So the force goes up really slowly at the beginning, and then it turns a corner, and it goes up a lot faster until it gets to the top where the die is closed, and then it drops down. Why isn't it constant? There are 4 reasons.
Surface area of the material that's fitting to the mold.
Okay, so the surface area is increasing, so to achieve the flow stress with an increasing area, we have to increase the force. All right.
No, it bottoms out. It's
Okay, it's a very
dimension
yes, and it is bottoming out against
on the flash.
it is bottoming out against the flash, which is already cold, and so that has a much higher strength. So that's reason number 2.
Is it strain hardening at all?
Number 3, it is strain hardening because it's happening so fast. All right, maybe there are 5. 2 more.
Stress egg!
Stress egg, that is exactly right. All of you right in here, simultaneously. It is so cool that you all answered stress egg. So when you start out, it is compressing it in one direction, right? Compressing in one direction. When you get near the end, you're compressing it from all directions at the same time. So you have moved from sigma F over to 1.414. Easy for me to say. 1.414 sigma F. So stress egg, excellent. And then the last one. Friction.
Friction!
Right, friction. The amount of contact area is going up. And so as it goes up, you're getting more friction rubbing against the walls, and that is increasing the rate at which you move to the 1.15 sigma F. So we're just riding the stress egg. That's all we do. Ride the stress egg, or the kite, but really the egg's cooler.
And then you do that for like 8 hours a day, standing in front of that thing.
Watch the video.
All of these
The-
videos that we're
well,
watching,
the
it's like, how do
egg is
people
the-
like have these jobs and not like go crazy?
So when I worked at CAT, there was a guy who was on the production line that I worked with a lot because he was helping to bring in a new process. And I said to him one time, Kerry, your job would just drive me nuts. How do you stand there? Because he worked 8 hours a day, and then anytime there was an opportunity for overtime, he would work it. So he worked most weekends, either 1 or 2 days. He just did that all the time. And for like 4 years. He had run the same grinding process for 4 years. How do you do that? He said, I just love it. You just stand there and you're always trying to make the process better, but while it's happening, your mind can just wander, you can think about whatever. That is great. I am glad that you like doing it. Tough way to kill. It was so hard. Anyway. Okay, we are going to watch how nuts and bolts are made with our happy Canadian friends.
Yes.
So that's good.
I love Canadians.
So our happy Canadian friends are going to tell us how nuts and bolts are made. And what I want you to look for in this is I want to know the answer to the question, why were the bolts, the heads of the bolts made in several steps? And I want to know why, how, when, where, whatever for.
You're trying to make me feel better.
I am. I want to know the reason that the nuts are formed hot and the bolts are made cold. Alright, so as we watch this, and they don't explain this in the video, this is just you.
The friction.
We have to discern these things, not guess.
It's estimating.
It's only estimating after you've seen
Nuts and bolts are made from what's called steel wire rod. After spending up to 30 hours in a furnace to soften it enough to be worked, the wire rod goes into a bath of sulfuric acid to remove any rust particles. It's rinsed in water, then coated with phosphate, a chemical compound. This prevents the steel from rusting before the bolt forming begins, and lubricates the steel to make forming easier. They form the bolts by cold forging, shaping the steel at room temperature by forcing it through various dies at high pressure. The forming machine first straightens the wire rod, then cuts it into pieces slightly longer than the bolt length. The extra will become the bolt head. Each piece goes through a die that makes it perfectly round, then through a series of dies that progressively shape the head of the bolt on one end. The machine heads up to 300 bolts per minute. Here's what the heading stages look like in slow motion. This die creates a slight collar. The next one turns it into a round head. Then the last die transforms that into a hexagonal head, the most common shape. Next, the machine forms the opposite end of the bolt. A tool called the pointer shapes the bottom of each bolt, creating what's called the chamfer, the part the nut catches onto. Here's the bolt before and after the chamfer. The bolt needs threads to enable the nut to screw onto it. Once again, they use the cold forging method. High-pressure rollers press in the thread pattern, as we see here in slow motion. This is the actual speed, up to 300 bolts per minute. During each production run, they take several samples to verify dimensions. They use various measuring devices, a micrometer to check the bolt's length, calipers to measure the width of the head, and a ring gauge to check the threads. To make the nuts, they use a process called hot forging. They cut steel bars into small pieces known as slugs, then heat them to 1200 degrees Celsius to make them malleable. As we we see here in slow motion, hydraulic hammers punch the slugs into hexagons, while a die pierces the hole. Then a tool called a tapper drives into the hole to cut the threads. That black liquid is a lubricant oil to minimize the wear and tear on the tappers. The nuts and bolts now go into an oven at 870 degrees Celsius for about an hour. This gives them the required strength. Then a rapid cooling in oil for 5 minutes solidifies the steel's internal structure. By now, the steel is hard but brittle, so they heat the nuts and bolts for another hour. This removes their brittleness, yet maintains their strength. The quality control team pulls samples off the line, measuring how much force it takes to break them. If a bolt meets its minimum strength requirement, it passes inspection, provided the break occurred in the threading, the weakest part. Finally, packaging, labeled among other things by size and grade.
When they say grade, like, this one's super strong.
Yeah, it's like, did the bolt get an A or an F? No, there are grades of bolts, which is a guaranteed strength. So like, if you need a high strength bolt on an automobile, you would use a grade 8 bolt. You can tell the grade by the markings on the top. They indicate the grade, which is the overall strength of the bolt. So not all of a similar size are the same strength.
When we were looking at the flange, and we were looking at the, or I guess it wasn't indented, it was raised lettering, and it was like 2A. Would that mean it was like size 2, grade A?
No.
Okay. Sorry for trying.
It was, it is, the size is based on the mean diameter and the number of threads per inch. We'll talk about that later. And so I'm not sure what the 2A was. Yeah.
Cool.
Okay. Why did they cold roll the threads, but on the bolt, but cut the threads on the nut?
They cold rolled the bolts because they wanted to do the thing with the grains where they like go with the
Okay.
ends.
All right. So why'd they stop halfway? I mean, they went all out for the bolts.
Actually,
Are they like, I'm just
couldn't,
tired now?
Cold roll the inside of the bolt, could you? Or the nut, could you?
You could. It is harder to do,
'Cause it's
certainly.
harder to
Is it because it's harder?
No, it isn't.
Shoot.
Yeah.
Does it have something to do with where you want the part to fail in the event of it being stressed?
So that it could be part of it that you, well, except that you're making the nut weaker by cutting it and it doesn't fail on the nut.
Is it because it doesn't fail on the nut, so it doesn't matter?
Yeah, that's what I
Or
was
why
thinking.
doesn't it fail on the nut?
It's just an attachment, it's not, the bolt goes into everything.
The nut's just there.
The nut just
So
goes.
the reason is because the bolt is constrained in size, right? The bolt can only be as big as the hole is. But the nut that goes on it, if you need it to be stronger, you just make the nut bigger.
Oh.
So it's
Duh.
easier to cut the threads than it is to roll the threads on the nut. And so you just make the nut a little bit bigger because that's easier to do.
How do you roll the ins? How would you roll the inside of a nut?
So you use something that looks like the tap that cut it, but it is undersized and it spins and interpolates as it goes around, and it pushes against the sides really hard. It is not easy to do, and so that is some of why they don't do it. All right, why did they form the heads of the bolt in multiple steps?
I think just through the process and the forces that were coinciding with the next process, like to put a shoulder on it, smash it flat. Because if you just smash it flat in one go, I think it'd be kind of hard to hit that mark really easily.
Okay, so it'd be hard to get the right
A little
shape.
A little barrel on it would be easier.
Okay.
Stress egg.
Yes, that's what I was
Stress egg. There could be some with the stress egg, that's true. I'm not actually sure that it's the best answer this time, but it's always a good answer. It's always a good answer, yeah.
Is it because of how, like what you said earlier about giving it time to get out of the strain hardening and then so it can form again?
It would be, except that it's not hot at that point. It was cold work by then. It was cold forging.
Friction.
So, friction?
Stress.
Constancy of volume? It's gotta be one of these. You're limited in the amount of ductility that you have, and so you have to apply it really carefully because you only have like 30% ductility in moving the part around. And so by the way that they preformed it, they could control where the material was deforming, from where the material was deforming, so that it would, that you wouldn't exceed the amount of strain that you have available in the material and fracture it. All right, that's how nuts and bolts are made. The one that they broke, even though that certified the lot, I'm hoping they don't sell that one. I don't know. Okay.
This is the only bolt that was certified.
It failed, it's certified.
Then you can have it
can't
now.
just apply it to the other one for you to test it.
You can
It
either
has
have,
all of them.
Never broken one or no
It's
one?
the only failed bolts are certified.
you can have the certified bolt or the whole bolt. All right. So, come on, there we go. 5 till, so 11 o'clock, whatever time of day it is.
I'm gonna go make Nikki mad.
Yes.
I thought you were doing that for the day.
Do it again.